Test.
Live. Good morning, everyone. Welcome. We have on the big screen here. This came in my mailbox yesterday. So, 250 subscribers, we get the certificate suitable for framing from somebody. So we're well on our way now to influencers. I don't know how much we will have, but ad revenue is just going to start rolling in. As you know, we're not interested in that at all. We're giving you this for free. And in the fall, we will even talk to YouTube and remove the ads that I'm sure annoy you come up in the middle. UC has their own YouTube official channel, and we can somehow make a sub channel for chemistry if this is going to happen regularly. So it'll be much more convenient for everyone in the future. Thank you guys for being the guinea pigs for a certain extent. If this goes forward. So we were talking last time about acids and bases. So we've come to a new subject. It's an important one because of all the chemistry that happens in your body. Many of you are going into the life sciences, and the chemistry that happens in your body happens in a buffered environment. We're going to learn what buffers are and how the pH that's maintained in your cells and your blood is vital for life itself, and the structure of the proteins and the DNA that make your cells go. So this is an important subject for many of you. It's a relatively straightforward because we understand equilibria very well now. So it's going to be applications, a special application of equilibria. We're going to give people a few minutes to show up here. We have the midterm Bonus question coming up, coming up in a few minutes. I think it's the next slide, and we'll give you guys some time to do that. I want to give people time, the late arrivers time to get here. We had, one of the reasons I'm rushing around here at the end is we took until the last minute to decide which one to put up here, and then making the slide was, we picked a complicated one, so I had to make the slide in 5 seconds. So, but we got that wrapped up and ready to go. So if you guys are ready to go, we will show you, I think it's the next slide here. So this information was on your exam. One of the first questions, a table of bond energies and some various reactions. And from that information, we asked you to calculate the bond energy of a YY bond. So from this information here, see if you can do that. They all say, well, there's how fast I was. I was, I'll put ABC. It's A, B, C, D, E, but that's how fast I was doing the editing this morning. I'll start the poll. You're in your Zoom rooms. Turn on your mics, talk about this, get the right answer. If you understand it, explain, talk through it. We're going to give you a few minutes here, so you'll have time to work through it. There is a calculation to do. So I'll start the poll here, and you can work on that. There we go. And I will make this more clear. A, B, C, D, E, D, Okay, guys, keep going here. So, as I said, I was typing this so fast this morning that I actually fat fingered the answers. The exact answer is in here. Pick the closest answer to the one you are calculating. So, just a couple typos. Sorry. I literally was doing this in my sweatpants and skipped the shower and came running in here 2 minutes before. Pick the closest answer and you will be all right. Okay, guys. I'll say this again. There was a typo. The closest answer is here. Pick the answer closest to what you're getting in your calculation. And enter that. This was rushed on our part. We apologize. And we are double checking the math here. in the room, but we're pretty sure if you enter the answer closest to what you get, that works. Are we good? Everybody confident? Only 87 of you. Are there any more out there? Many more took that than there are many more who took the actual midterm. But that's okay. You don't have to come to the live stream. Okay, let's see what you're thinking. 87 has been there for a while. 88, anybody else gonna push their button? Push now, because I'm gonna stop it in 3, 2, 1. Stopping the voting. And everybody says they're thinking the last one, E, is the answer. I think it's actually 640-ish and not 630-ish, I think is what we got. That was a typo this morning, but that was the closest answer to what was there. So how were you supposed to do that? Let's go through that together and see if we get the correct number. So the idea here was you were given some values of bond energies on the table. So you were given bonds with X. So an XX bond, X with X, has a value of 230 kilojoules per mole from the table. And you guys all got different numbers. That was randomized on the exam. And Y with X is 320. So an XY bond has a value of 320 kilojoules per mole. So with that information and this information, can you get there? And you were meant to recognize that here's an XX bond, and here are 6. So there's some compound that has 3 XF bonds in it. So there are 6 total X. I'm saying F now for some reason. Oh, because yeah, Y was a stand-in for fluorine. I keep doing it. Y. So XY bonds, and you want to know these. So you know, though, that the bonds, we can set this equal to this. We can do a bonds broken minus bonds formed, break all those bonds, form all those bonds. That should equal 250 kilojoules per mole. So we can do that. On the whiteboard, I guess. Let's go through that calculation. So we have an X2 plus 3 Y2s is going to give us 2 XY3 molecules. So the bonds I break are 1 mole of X2 bonds plus 3 moles of Y2 bonds. And then I'm going to subtract away the bonds I formed, and that's 6 times XY bonds, and that has to equal 250 kilojoules per mole, because this is delta H for the reaction. So this number here was 230 plus 3 YYs minus 6, and the XY bond was 320, and that had to equal 250 kilojoules per mole. So 3 YY bonds have a value of 250 plus 6 times 320 minus 230 divided by 3 will get us to 1 YY bond. So that's calculation we wanted you to do, and people are telling me that's around 640 something ish kilojoules per mole. Okay, so well done. It sounds like most of you got that, and I'm glad everyone here told us that people were talking about it together in their rooms. We talked about it here. One good time to come to lecture is, there won't be any more of these, I guess, is the day after the or when the midterm bonus, because then you get to talk to me. Bonds formed, bond energies equating with bond enthalpies was the idea here, and you guys got that at the second time around for sure, and many of you got it also on the first time around. So we'll go back. And let's continue with what we were talking about. Very quick review of just the end of yesterday. We talked about acid-base conjugate pairs. So something that acts like an acid is a proton donor. And we talked about various proton donors, acids. So HA could be any one of those. And these are the stronger of those, the more likely, the ones that have the larger K for this reaction are here. The ones that can act as the A minus, that is this thing minus a proton. And of course, the charge for that would be minus, but these charges are different. This one goes from plus to neutral as you donate a proton. So that pair, H₃O plus and H₂O, have a conjugate acid-base pair relationship. And the conjugate bases are written here, and those go stronger in that direction. So the stronger your conjugate acid, the weaker your conjugate base. Strong aligns with weak. And we did that with the base as well, and said we could write the same kind of relationships for bases. So we go through that quickly because we talked about, that's where we ended up yesterday. We wanted to talk about that happening for the general case. So the general case, we would write the equilibrium expression, and the general case is an acid in water. So if we put one of these acids or bases in water, we can write an equilibrium expression. And when we write that equilibrium expression, we have products. The H₃O plus ion is formed because the acid donates a proton to a water molecule that's there. It leaves behind an A minus. The reactants are the HA and water, but water's the pure liquid, does not appear in the equilibrium expression. So we're back to well-known territory, equilibria, with a different context of acids and bases, proton exchange reactions. In this case, water is going to act as the acid because this base is something that accepts protons. And what's around to accept a proton from? Well, the water. So it'll accept a proton from the water and make OH minuses because a proton comes off your water. It ends up on the base. So these bases are bouncing into these waters, and some of them pull a proton off the water. And remember, when I say proton, I'm talking about H plus, and sometimes even talking about H₃O plus, because that's where the proton ends up frequently. So H plus, proton, I will use those interchangeably. The proton moves from the water to the base because the base is something that accepts protons. You can imagine it happening in solution, water and the base bumping into each other. Some of those collisions result in the base taking a proton. How many of them result in a successful exchange? Is there a number that would tell me about how many? Yes, the value of Kb tells you about how many. The ratio of those successful collisions give you a proton ending up on the base. Same thing for the water. An acid bumps into the water, but this time it gives the proton to the water. How many times does that successfully happen? Dictated by the free energy of the reaction and therefore the K, the equilibrium constant of the acid-base equilibrium. Interestingly, water, as we saw in our review there, water can act as an acid or a base. So in solution, that can happen as water bumps into water. Sometimes you'll get a one of the protons exchanging. So you'll end up with an H₃O plus and an OH minus because a proton exchanged between two water molecules. And you would write that equilibrium expression as products over reactants, but the reactants again are the pure liquid water, so they don't appear in the equilibrium expression. And that K is H₃O plus times OH minus concentrations. So that we give another special symbol, Kw, the auto-ionization constant for water. How prevalent is that in water? The size of the K tells you. And that K is extremely small. It's 10 to the minus 14. So this barely happens in water. But we take it into account. And why is it important to take into account? Because everything you do in water, all the equilibrium expressions have to be satisfied at the same time. That means this equilibrium is always satisfied in liquid water. No matter what else you put in there, those equilibria will all be satisfied simultaneously. So in water, no matter what you do, the product of the H₃O plus concentration and the OH minus concentration must be 10 to the minus 14. If you take nothing else home from Chem 1A, take home the fact that if you do something in water, the product of the H₃O plus concentration and the OH minus concentration must be 10 to the minus 14. And of course, Ks are a function of temperature. So that's at 25 degrees. That's what that must be. It's not a very strong function of temperature. This one doesn't change very much, but a little bit. So there's another thing you can take to the bank. Use that to your advantage. There aren't many things you can take to the bank. That's one of them. So in pure liquid water where nothing else is happening, those concentrations will just be equal. So H₃O plus and OH minus each 10 to the minus 7. So the product of them is 10 to the minus 14. We're going to define then something called the pH to essentially to make these numbers easy to work with. It's a pain to say 10 to the minus 7 or 1 times 10 to the minus 7 all the time. It's easier just to say 7. So we're lazy. That's what we do. So let's look at what that is. We're going to define this thing called the pH scale. But you could define it for anything. The little p essentially means take the minus logarithm of the quantity. So px means minus log of the x concentration. I know you guys don't learn about logarithms anymore in school, so you're going to have to review a little bit. But the general expression is something you should know. So if I'm talking about pH, and again, I'm just talking about H plus, the proton, H plus and H₃O plus, same thing in water. H₃O plus concentration. So the minus log of the H₃O plus concentration is what gives us this pH scale. And it's not, logs aren't complicated, and we'll see why we have to do it in a minute. But if you, when you say log, in this case, we're talking log base 10. We talked a little earlier with the natural log, that was log base E. So if you have log base E, the exponential, this we abbreviate as natural log, ln. But if you're taking log of some number, A, that gives you some number B. What is the relationship? Well, it's this base to this power has to equal that number. So that means that 10, in this case, the base is 10, log base 10, to this power has to equal that number. So B equals A. Basically, it says take the exponent of the base 10. And that's what your value is. So it's simpler than it looks. If you have log of 10 to the minus 7 equals minus 7. It's just take the exponent is what you're doing. So it's actually a very simple thing. It allows us to talk about just the exponent rather than the writing it out as 10 to the minus 7. We do the minus log. So if H₃O plus and OH minus is 10 to the minus 7, then pH is minus log of that number. Log of that number is minus 7. Minus log of that number is 7. So basically, you take the exponent, and that's the pH. You have to worry about, if this number isn't 1, then you have to worry about the log of that number too. But for simple things, 10 to the 7, the pH is 7. If you have different concentrations, so let's say the OH minus concentration is very small, 10 to the minus 14th. So it's mostly H₃O plus. That ratio, also the product of those is still 10 to the minus 14. So that's fine. I can do that. What is the pH there? Well, the pH is minus log of this number. In this case, the exponent is 0. So we have a pH 0. That's a highly basic solution. It's highly Why did I write basic there? Oops. That's a highly acidic solution. Let's change that with our pen. That's going to go away in a second. This solution, it's mostly H₃O plus. That's the high concentration. OH minus is the low concentration. So low values of pH are acidic. So this is the acidic end of the scale here. This is neutral here in the middle where the concentrations are equal. And I'm going to bet that I've got, I probably have highly acidic up here. This is minus log of this number. So the exponent, 14, that's pH 14. And that is highly basic. All kinds of typos this morning. That is the disadvantage of PowerPoint. If you have a typo, it shows up dramatically. So let's have it up there, right? So you guys can get it correct in your notes. I think in your notes, I didn't even put those. I think I altered this after I made the notes. I'm not sure when I printed out the notes. So those might not even be in the handout. This is a late add, which is why it's wrong. Edited at the last minute. Okay. Great. So we understand this pH scale. It's a relatively simple thing. Take the exponent of your base 10 exponent number, and you have the scale. Just makes it easier to talk about. It's also, here's crucially why we do it. If you had to graph this range is 10 to the, 10, 0, up to 10 to the minus 14, or 10 to the minus 14 to 0. If you have to plot that, your graph paper isn't big enough to do 0 to 10,000 billion. Okay. So it's easier just to talk about a scale from 0 to 14 than a scale from 0 or from 10 to the minus 14 to 0. So it saves graph paper, basically. What we want to is another good thing, another good reason we do it. So here are a couple solutions. Which has the highest pH? We'll talk through this together. So I'm going to take 10 to the minus 3 molar NaOH, and that's a strong base. So K for this one, K for this dissociation is huge. This is a strong acid, 10 to the minus 6 molar HCl, and 10 to the minus 12th molar HCl, which has the highest pH. So we need to get the H₃O plus concentration, and we need to take the minus log of it. So 10 to the minus 3 molar sodium hydroxide, we have sodium hydroxide, the OH minus concentration will be 10 to the minus 3. How do I know that? Do I have it in the next animation, or should I write it down? I do not. Let me write it down. How do I know that? Well, I'm going to have, when I put NaOH in water, that completely ionizes. This is a salt to Na plus OH minus. I could write that in water, Na plus OH minus in water, H₂O. And what's going to happen there? All of these strong bases find water. If they do, Na plus doesn't do anything. It hangs around. If they do, you get the same product, because you'll get H₂O plus OH minus. So that concentration doesn't change going from one side to the other. If this bumps into a water, that becomes OH minus, and that becomes H₂O. So when you put sodium hydroxide in water, the concentration, the amount of NaOH, is equal to the concentration of that in the water, because that can't change. Even if it did bump into a water, you'd just make another one. That is a strong base, completely dissociates. That's a salt. You should just know that. Here's what's going to happen on the exam. You have to know some strong acids and some strong bases. Sodium hydroxide, strong base. Hydrochloric acid, strong acid. What does that mean to you? It means there's not a K. K is ginormous, and they totally dissociate. That's all it means. Practically on the exam, I'm going to give you K values. If you don't get a K value, you might be suspicious that that's a strong acid and you don't need the K value. It totally dissociates. So there are strong acids, totally dissociates, and weak acids that K is small, less than 1. And some of those you should remember. Hydrochloric acid I may not tell you on the exam that's a strong acid, totally dissociates. So please remember it. Sodium hydroxide, also a strong base. So that means the pH of this is 11, because if the OH minus concentration, it's also a minus sign missing there, is 10 to the minus 3, then the H₃O concentration must be, if it's in pure liquid water at 25 degrees C, must be 10 to the minus 11. Why? Because the product of those two things must be 10 to the minus 14. And you know, if you multiply two numbers with an exponent, you just add the exponents. So 10 to the minus 3 times 10 to the minus 11 is 10 to the minus 14. The pH is 11. It's just the minus log of that number. It's just the exponent there. The pH is always the H₃O plus concentration, not the OH minus concentration. So if you can calculate OH minus easily, then get to the H₃O plus, because those two are locked together. You can always get one from the other. What about 10 to the minus 6 HCl? This totally dissociates into H pluses and Cl minuses. And the same thing happens. That H plus ends up on a water. And you have H₃O plus 10 to the minus 6 concentration. So the pH of that, easy, 6. What about 10 to the minus 12 molar HCl? Well, you'd say, well, there's 10 to the minus 12 being added to the water to make H₃O plus at 10 to the minus 12. But that's a silly situation, because when you added this to the water, the H₃O concentration was already 10 to the minus 7. So 10,000 times bigger than that. So if you add just 1/10,000th more to this, you don't change this number. Basically, what we're saying is 10 to the minus 7 plus more from the reaction, 10 to the minus 12. When you add those things, that number is still 10 to the minus 7. Right? Because this is 0.00007, but this one is 0.0000001. So the sum of those two numbers is still 10 to the minus 7. So the pH is still the pH of water. Basically, what this says is, this should make sense to you if you think about it logically, 10 to the minus 12th molar. How do you even get that? How do you get 10 to the minus 12th moles of, it's like a fleck, I mean, it's a fleck you couldn't even see, some kind of picogram of HCl dropped into your liquid water. Would that change the pH? No. So that's the rational way to say that. That doesn't change the pH. So the pH of the liquid water stays the same. Which among those is the highest pH? Is that what I asked? Highest? I forget. Well, highest is that one. Lowest is that one. Forget what the question was. Was it highest or lowest? Let's see. It was highest pH. Okay. So KW for liquid water versus temperature. Now this is interesting because I'm showing you the plot of KW for water for various temperatures. So at 25 degrees C, we have that value. At 60 degrees C, we have that value. And all these values are multiplied times 10 to the minus 14. So that value we know, 1 times 10 to the minus 14 is KW there. And you can see, go up to 60 degrees, it increases by a factor of 10. So it's 10 to the minus 13 here, it's 10 to the minus 14 there when I get up to 60 degrees. So what's the pH of hot water? Let's talk about it together. The pH of hot water, KW for H2 at 60 degrees, is around 10 to the minus 13. that means the H₃O plus concentration times the OH minus concentration is 10 to the minus 13 when you're at higher concentration, or you're at higher temperature. So those concentrations, though, have to be equal. I need the H₃O plus concentration to get the pH. So I need to get H₃O plus to get the pH, because I want to take the minus log of that number. Well, the concentrations are going to be equal. So the H₃O plus concentration is going to be equal, that is going to be 10 to the minus 6.5. I mean, we don't usually write fractional exponents, but here it's just convenient. I know because the product H₃O plus times OH minus. So if this is 10 to the minus 6.5 and this is 10 to the minus 6.5, the product of those is 10 to the minus 13. So I can say that, and then that makes the math easy, because to get the pH is the opposite sign of that exponent. So the pH is 6.5. So what's the pH of hot water? Less than 7. Minus log of that is 6.5. So there we go. There's K versus T. You should also be able to tell me, is that reaction auto-dissociation of water endothermic or exothermic? You should probably have some kind of idea about that, because what we have there is a K that increases with temperature. Okay, let's start mixing them together. We're going to mix together a strong acid and a strong base. If you start out with 0.1 molar HCl, all of that, every single one of those protons comes off the HCl. This totally dissociates. It's a strong acid. You will not have a K infinite. So K infinite means every single proton comes off and ends up on a water. So if that concentration initially is, you put in 0.1 moles of HCl to 1 liter of water, all the protons come off, and the H₃O plus concentration in your water is 0.1, which is 10 to the minus 1. So what's the pH? It's the exponent with the opposite sign, 1. Okay, so this thing starts out at pH 1. And just go back one animation there. That is what that is. Now I'm going to add this axis here. I'm going to add some moles of base. And as I add OH minus, and I would do that by, say, a sodium hydroxide solution, you could add little chunks of sodium hydroxide. So you're making OH minuses in solution. Those react with your H pluses. And the pH will increase, because as you add more of those, they will eventually use up all your H₃O pluses and give you waters. So the reaction that's happening is your H₃O pluses, which came from here, are going to react with your concentrate. I'm just writing the concentrations here, with your OH minuses from here, but that going to H₂O, the K for that is ginormous, 10 to the plus 14. That's the opposite of the direction we wrote it for. We know in this direction, that's auto-ionization. So that is 10 to the minus 14. This, going the other direction, is 10 to the plus 14. So that goes all the way. Whenever one of those finds one of those, it makes a water, and that starts to neutralize the solution. This concentration goes down dramatically. Those just disappear. There are excess of these to start with. Tons more of those. As you start adding those, every one of those just starts taking one of those away and making water. So it neutralizes the solution step by step. The pH heads up towards 7. This concentration goes down. That means pH goes up. When you get to the point where you've added 0.1 moles, that will react with the entire 0.1 mole that you added to your 1 liter of water to start with. So 0.1 moles of OH minus will use up all of them. So you've added 1 mole of H₃O plus for every, you've added 1 mole of OH minus for every 1 mole of H₃O plus that was there. That neutralizes them. All your H₃O plus is used up. So you're in the situation where the product of those two, H₃O plus, OH minus, still has to be 10 to the minus 7. So the equal point, equivalence point in that case, is both concentrations, HCl plus and OH minus, are 10 to the minus 7. So the pH is 7. Then when you start adding more of this, now you've used up all this. So now you're going to build up OH minus. And as you build up OH minus, the H, I'm going to write that down here. So all the time, H₃O plus and OH minus must be, the product of those things must be 10 to the minus 14 all the time. So here, you started out with that was 0.1. That's 10 to the minus 1. So this must have been 10 to the minus 13, initial state. So that's where you started, 10 to the minus 1 and 10 to the minus 13. pH 1. It's minus log of that number. That's what you get the pH from. And then you start adding this, and by the time you've added an equal amount of that for every one of this, so when you've added 0.1 moles of that, then you're at the situation where there are both 10 to the minus 7. So you can make this go, you can add those guys, use up all of those, but you can't make the concentration go less than 10 to the minus 7 until you add excess. So when you get equal, this doesn't go to 0, it goes to 10 to the minus 7. So the concentration didn't go entirely away because the product always has to equal 10 to the minus 14. And then when you start adding more of this, then that gets bigger, and this gets smaller. But this number determines the pH, so the pH goes from 1 to 7 when you've added equal amounts, and then to 13 as you get to excess base. So that's the description of what we call titration curve, and we're going to look at those till you're sick of them. You can do that in the opposite direction. Say you started with 10 to the minus 1 molar base. That means 10 to the minus 13 molar H₃O plus, so pH 13, and you add acid in this case, the mirror image would happen, the reverse would happen. You would still get to a point halfway through where you've added 1 mole of acid for every mole of base, to what we call the equivalence point, where you've added an equal amount of acid and base, and in that case, this pH is 7. Strong acid, strong base titration. Okay, let's do this one. You can talk about this in your breakout rooms. Here's the titration curve for HCl with 0.1 molar NaOH. And it's just schematic. Oops. What if I do the same thing, start at the same place, but instead titrate with 0.2 molar NaOH? And we're adding the volume of NaOH we add is on the x-axis there. What happens in that case? Think about that. There's 3 options here in your breakout room, and we'll take a vote. Yes, do your vote. Okay, let's come back together. Push a button if you have not yet done so. Let's see what you're thinking. Just under half of us are thinking C. I agree with the C's. That's the same conclusion we came to here in the studio. Why is that? Well, we said that I'm going to titrate the same solution twice. I'm going to do its HCl once with 0.1 molar NaOH, then again start out from the beginning at 0.2 molar NaOH. So the initial point is the same. So that kind of rules out A altogether. So what's the difference between these two? Well, the difference between these two is the final pH is higher, or the final pH is the same-ish, but the equivalence point is different. So the green one reaches equivalence sooner than the yellow one. And what is equivalence point? Well, the equivalence point is when I've added a mole of base for every mole of acid I've had in there. If you're plotting versus volume here, so this is milliliters of base, and I titrate with 0.1 molar base or 0.2 molar base. If I twice the concentration of base, for every drop I put in, I have twice as many moles of the base. So I'm adding moles of base faster per volume. That means I'll get enough moles of base to use up all my acid sooner, and I'll reach equivalence point sooner. So I think there's probably an animation that shows that. Equivalence point is reached with half the volume. So you'll get a titration curve that looks like that. And that is C. I should point out, it's very important that at every point on a titration curve, the reaction is at equilibrium. These are all equilibrium points. That was a question on the final exam a year ago. You know what I'm going to do on the exam. You know me now. I'm going to give you a titration curve with some points on it. And I'm going to ask you something about point A and point B and point C. And I'm going to say, at which point is equivalence? And you'll answer B. And then I'll say, at which point is the reaction at equilibrium? Mark all that apply. All those points are at equilibrium. Oh, you have to get in my head. Get in my head. And then take the exam. Okay. This is fun too. Let's see what you think about this. Here are titration curves. So your sodium X and sodium iodide, sodium bromide, or sodium chloride, and that totally dissociates. So that gives you 0.1 molar chloride ions, bromide ions, or iodide ions. And then you titrate it with silver nitrate. Now, you're putting silver nitrate ions in, and that changes the concentrations of the chlorine, bromine, and iodine, and we're taking minus log of the concentrations and plotting them. So what does that mean about the solubilities? Oh my God, everything's coming together at one time again, of silver chloride, silver bromide, or silver iodide. This is a a tough question to ask somebody who just learned what pH was or pX was 10 minutes ago. And you have to drag up everything you know about solubility from last time. So let's take a few minutes, talk about it in your groups, and we'll take a vote. Okay, guys, this is brutal. Come on up, and we'll see if we can figure it out. Initial thoughts.
I feel like we'd have to find the solubility numbers for iodine, bromine.
You want to look them up in a table or something?
Maybe we don't.
Well, I'm asking you to get them from the graph, but yes, I mean, that's what the question is, which is more soluble. But the point is you can get them from the graph. So let's try to do that. So write down just with your finger, what reaction are we talking about when we're talking about these solubility reactions? So write on the board, Ernesto, you can write on the board first. Right up there, right here, silver chloride, AgCl. And if I'm talking about that dissolving, give me an arrow, into silver ions and chloride ions, what does that look like? We're going to write it like a chemical reaction. Oops, I erased. Yes. AgCl goes to what? Ag pluses and Cl minuses. Plus Cl minus, okay? That is the reaction for which we want to know the K. So the more soluble has the bigger equilibrium constant. The more of this you form, the more soluble. That's how we define solubility. And if it's more soluble, what are the final concentrations of these guys? Higher or lower?
Lower.
If it's more soluble.
Oh, isn't it going to be higher initially?
Yeah.
And then it's going to react more? And
then... well, we haven't done any reaction yet. We're just on, let's say, just put this in water. You put this in water, the more soluble one makes more ions. That's what solubility means. You don't even have to think about a K, really. If it dissolves, you make a lot of ions. The solid goes away. So we have 3 of them.
So would the most soluble be the acidic ones or no?
Well, there's no acid here. So the most soluble are the ones that make, it's the same thing, most acidic, it's most soluble. The most soluble ones make the most, instead of acid, make the most chlorine, make the most ions. So this one, Br, that also can make Ag plus and Br minus, and the Agi can make Ag pluses and I minuses. So if you wanted to say, I start out with the concentration of chlorine, bromine, and iodine, and they're all the same, and why is that?
Oh, I have an idea.
Mm-hmm.
I think it could be chlorine because it goes to the least px,
which is the most X. You want to say acidic, but they're not acid. It's the PCl minus, and so it's what we're plotting there is minus log of Cl minus. So if this is 10, 11, and 12 over here, then what are the concentrations of Cl minus?
10.
That's the log, that's the Px. So if Px is 10, then the concentration of Cl or X is 10 to the minus 10. That's the relationship. Take that number and put it in the exponent, or take that exponent and put it there. So that's 10 to the minus 10 concentration. That's 10 to the minus 11. That's 10 to the minus 12. So when you're all...
So the top one's going to be the least because minus 12 is the least.
Yeah. but you said it right the first time. You said Cl's the most. So Cl ends up with the highest concentration. So if it's the highest concentration, then
It's the least soluble because it reacts.
no, the one with the highest concentration is the most soluble, ends up with the most Cl. If you end up with the high concentration over here, then your K is the biggest. Your solubility is the highest.
K is towards reactants.
Yeah, bigger K, more reactants.
Okay.
So higher K, what looks like we're saying is this has the biggest K because at the end it has the highest concentration. But if it has the biggest K, it's the most soluble. And we did ask for the least.
And when there's more ions, it's less soluble when there's more ions, it's more soluble.
Yeah, more ions, more soluble.
Okay.
It's kind of a simple thing. If this is breaking up, more of it dissolves, you get more ions. The trouble you're having associating it is how big is K? That's where you're kind of getting the mental block. If this makes more ions, it's more soluble. That's easy to understand. More ions means bigger K because means reactants stay here. Products are favored for bigger K. Products over reactants. Big K, lots of products, lots of ions.
My problem is
one of your problems. Oh, that was so mean.
It's okay. Okay, one of them is so this is a smaller number, which means that there's less ions, which means
yes,
it reacted, which means
it went more this way.
But doesn't that make it the least soluble?
Yeah.
Is this the answer?
Yeah.
Oh. It's not even one of my problems.
Yeah, it's not even one of my problems. I got problems that aren't even problems. What? Oh.
Oh my God.
The whole time? Or just the last second? Did I hit? Sorry. Welcome back, everyone. I came back a little earlier than I thought, and we were joking around here a little bit. So I hope I didn't want to embarrass anyone who we were joking around with. So let's see what you're thinking. After all this is a tough one, as I said, equally split between A and C. And I can understand why. We were doing the same thing, going back and forth between A and C. I forget if I have a good animations here. It's not very good, so I'll write a little more on the board here. So what we see here is we started out with sodium X, NaX, and I told you that was very soluble. So you got that totally dissociates into Na pluses plus X minus. And X is either Cl, Br, or iodine. So initially, all the ion concentrations are the same. And then you start adding silver nitrate, AgNO3, and you get Ag ions and nitrate ions. And now these two things are in solution together. The silver and the nitrate, or the silver and the ion. And these two things won't react, sodium and nitrate. That's also super soluble. So it's silver and nitrate, but you know I could write AgX, whether it's chlorine, bromine, or iodine, goes to Ag plus X minus. This equilibrium has to hold now too. And that's the equilibrium that's driving the reduction in the concentration of these guys. Silvers are going to find your X's and they're going to make the solid silver X, silver chloride, silver bromide, or silver iodide, provided that this isn't very soluble, provided that the reaction does go this way. And that means if it's not very soluble, this precipitates out of solution. So this reaction would go that way if these guys are insoluble. And they all are insoluble. We can tell because silver chloride starts being formed, and that lowers the chloride concentration. Silver iodide starts being formed, and that lowers the iodine concentration. So the concentrations of the ions are being lowered because these salts are precipitating out. They're forming the solid. The reverse reaction is going. So it's a titration. You're removing X instead of removing H₃O pluses. You're removing ions, but you can still plot minus log of the ion concentration. So here this is minus log of the ion concentration, which we call px. We call it pH if it was the H plus concentration. So these are some numbers. Let's just, we don't know what they are, but let's just say this is 10, 11, and 12. So if P of the Cl concentration is 10, what is the Cl concentration? Well, you know how to do the conversion. The Cl concentration must be 10 to the minus 10. And the iodine concentration, so the bromine concentration must be 10 to the minus 11 because it is px11. Iodine concentration must be 10 to the minus 12. So I can convert from px to X concentration because I know the relationship, minus log. Basically, it says, take that number and put it as the negative exponent. Take that number, put it as the negative exponent. Take that number, put it as the negative exponent. That number is the negative exponent. So I can get the concentrations at equilibrium. So which has the lowest concentration of ions at equilibrium? Iodine, 10 to the minus 12th. So that means when iodine is here, the reaction goes furthest to this side. It's the least soluble of those salts. Whew. If you understand that, I hope I said most of it right, and you can go back and listen to the, watch the YouTube after the fact. I go watch the YouTubes after the fact. I don't watch them all. And you guys should do this too. You know, on YouTube, you can just turn the speed of playback up to like 5 or something. Just turn it up to 2 and go through that really fast. See if you understand that. Review that, because this is everything. This is our solubility. If I asked you to rank, here's how it might look on the exam. Rank KSP for those 3. How would you rank the solubility products, the K for that reaction? Well, this has the smallest, this has the medium, and this has the biggest KSP. That is the least soluble, smallest KSP. This is the most soluble. None of them are very soluble. All the Ks are less than 1. But that's the most, and that's the least. I'm sorry, that's the least. That's the most soluble. That's what you have to watch out for, because I go back through and I watch clips of these things, and I do misspeak from time to time. Not a ton, thankfully, but I usually catch every other lecture or so, I catch something that I just say backwards. So ask your GSIs. They always say it forwards. Okay, so high px means a low X concentration. Low X concentration means low solubility, was the take-home lesson there. But a lot, everything we've talked about for the last 2 days in that expression. Okay, these are just some calculations, so we'll just skip over this. We'll stop for today, and we'll pick up this tomorrow. These calculations, I think, are in your notes. I won't even go through them. Tomorrow we'll start with the next topic tomorrow morning. So we'll see you tomorrow, bright and early in Berkeley, California. The results of your exams are now posted. You're going to see three things, three new entries in the gradebook, I think. Lillian isn't here. Lillian, if you're watching, tell us if it is actually happened, if you have updated the gradebook. If you're in the Zoom or you can hear us and just text us. Lillian is updating the gradebook. She's putting the score for your midterm, and it might change because we manually graded some questions. And then the three questions that we manually graded, and they were the fill in the blank questions, those will appear as separate entities, questions 4, 5, and 6 on the exam, I think they were. So you'll get a score, a 0 or a 1 for questions 4, 5, or 6, so you know, and then you'll get your total score. And then we're gonna release we'll release the answers and everything. The answers go on tomorrow morning, and but we'll release everything. So you'll be able to see all the questions, all the answers, all the right stuff soon. We'll release the quizzes to you today, so you can at least look at them. I'm getting texts, so those from Lillian. Also, I update. Maybe I can just read you the text from Lillian in real time. So, updated midterm 3 and B courses seems to be giving points. Oh, maybe she's having a little trouble. So I took points with a little. Okay, we'll make sure it's all right by this afternoon. Lillian is currently working on it. Looks like there was a minor issue, but I think she's fixed it. So you'll be able to see all that updated stuff this afternoon. Okay, take care. See you tomorrow.